Thank you for inviting me here and giving me a chance to speak about my work. So yeah, I'll be talking about that. Whoops. And so I'll start with the classical case, which by that I just mean the case of a discrete group. And so to sort of motivate what I want to talk about later, let's begin with this. So here G is a discrete group, and it'll always be a discrete group throughout this talk. And here I'm concerned about the reduced C-star algebra of G, which is the C-star algebra generated by the left regular representation, represented on L2 of G. Okay? And we have this notion of group dynamics. And basically when I'm talking about group dynamics, I'm talking about it in this setting, in this framework where we have unital G C-star algebras, which are unital C-star algebras for which G is acting on by star automorphisms. And we consider this category equipped with the morphisms of G-invariant unital completely positive maps. So they're maps that respect the group actions. Okay? And in this category, we have the special class of G C-star algebras, G boundaries. And so I'll talk a bit more about the definition of that later. But an example to sort of have in mind is the Gromov boundary of, say, the free group on 2 generators or n generators. Basically, this is just the set of all infinite words. So say you're looking at all of the words and you go off to all the infinite ones, that's the boundary, the Gromov boundary of the free group. Okay? So we have this notion of a G boundary and there is this sort of universal object in the category of G boundaries. It's the Furstenberg boundary, and it's constructed as the G-injective envelope of the trivial action. Okay, so these are sort of important things for group dynamics. Okay, and there's a very particular G C-star algebra I'm interested in. It's the reduced C-star algebra. So G acts on it by this conjugation action by the group unitaries. Okay, okay. So now let's take a state on the reduced C-star algebra. So I use this to denote the states on C-star algebras. And it turns out that a state is tracial if and only if it's G-invariant, which means that it's invariant by this conjugation action on the reduced C-star algebra. So what this is saying is that traciality is characterized by this nice group dynamical characterization. And so what this means is when you're looking at the structure of the tracial states on the reduced C-star algebra, you can use group dynamics to sort of, the machinery of group dynamics to say interesting things about this, about the tracial states. Okay? And just sort of an important subclass of the tracial states are the idempotent tracial states. And it turns out that these are in correspondence with normal amenable subgroups of G. And in particular, they have this form. So they look like indicator functions on the normal subgroups. And by this notation, I mean that if you restrict to the copy of G inside the reduced C-star algebra, it's the indicator function on it. So, and functionals on the reduced C-star algebra are completely determined by the functions that you generate, that you get when you restrict to the copy of G. Okay. So this is sort of the general framework for this. And for a bit more notation, I denote the sort of trivial idempotent tracial state by that. And this is also usually known as the canonical trace on the reduced C-star algebra. It actually turns out to be the Haar state in a quantum group sense. Okay. Okay, so now let's sort of illustrate what you can do with group dynamics. Let's take a tracial state on the reduced C-star algebra. By G-injectivity of the Furstenberg boundary, we can find a G-equivariant extension to the reduced cross product of the Furstenberg boundary with G to the Furstenberg boundary. And then by using some extra categorical properties of the Furstenberg boundary, so in particular what you can show is that this actually ends up being a conditional expectation, and you can get the following results, which these are the sort of techniques that these guys used to get these results. You can show that a tracial state concentrates on the amenable radical, which is the largest normal amenable subgroup of G. And by that I mean it's supported only on the support of the tracial state is contained inside the amenable radical. And a way to rewrite this is, okay, so we have this natural algebra structure on the dual of the reduced C-star algebra, and I'll talk a bit more about that later. But you can realize the fact that the support of the trace is contained inside the support of the idempotent state we're associating with the amenable radical, by this sort of algebraic relation that, convolving tau against this idempotent tracial state just gives you back tau. Anyway. And so as a consequence, triviality of the amenable radical gives us the unique trace property of the reduced C-star algebra. And actually, the converse is pretty easy to see. Unique trace property implies these guys are equal, and that forces triviality of the amenable radical. So for example, group dynamics gives you a way to characterize the unique trace property of reduced C-star algebras. So that's sort of a nice thing that you can do. So I'm not exactly going to talk about a quantum analog of this exact result, but this is sort of to give you an idea of what you can do with group dynamics and the fact that the tracial states are G-invariant. Okay, so let's move on to quantum groups. So the setting that I'm going to sort of define things in is the Customers and Voss formulation of discrete quantum groups in terms of von Neumann algebras. So here, a discrete quantum group is given by the following information. So we have a von Neumann algebra, which decomposes into matrix algebras. And it's represented on some Hilbert space L2 of G. And actually L2 of G is coming from all of the Hilbert spaces that all of these matrix algebras are represented on. Okay. Kind of like the idea for that is, so in the case of a discrete group, L infinity of G is just bounded scalar valued functions. But here you're replacing the scalar values with matrices. That's kind of like the intuition for that. Okay. And we also have a coproduct, which is a von Neumann algebra morphism, so a normal unital star homomorphism that satisfies co-associativity. So this is sort of the associativity of a group multiplication, but you kind of reverse the arrows and you get this von Neumann algebraic realization of that. And then psi L and psi R are left and right Haar weights. So they're special normal semi-finite weights. I don't really want to get into the details of those things, but they satisfy certain left and right invariants respectively with respect to the coproduct. And in fact, say, take psi L, for example. L2 of G is the GNS construction from psi L, and this is something that generalizes, right? All right, so then the pre-dual of L infinity of G is known as the quantum group algebra, and we equip it with an algebra structure using convolution, which is defined using the coproduct. And it turns out to be a Banach algebra with this convolution algebra structure. All right. And then I denote C0 of G just to be the C0 direct sum of those matrix algebras that L infinity of G comes equipped with. And moreover, L infinity of G is just the multiplier algebra on top of C0 of G. Okay. So this is the basic framework for this. All right, well, it turns out that there exists a unitary that implements the coproduct. And by that I mean we have a unitary here that lives on this tensor product, such that you can write the coproduct as this through this conjugation formula with the unitary. And what you can do with this unitary is define this function, okay, and it ends up being a representation. And the unitary, of course, lives in an appropriate subspace of this, so that this formula makes sense, and we get a quantum analog of the left regular representation. And with that, you can define the reduced C-star algebra of discrete quantum groups. And we define it to be the C-star algebra generated by the quantum left regular representation. And the idea is with groups, you can take the left regular representation and linearize it through L1 of G and define the reduced C-star algebra that way. And so this is our approach here. And it turns out that the reduced C-star algebra is a compact quantum group C-star algebra. And that means that it comes equipped with its own C-star algebraic version of a coproduct. In particular, that means its dual space is a convolution algebra. And also it comes with a Haar state. So there's a state on the reduced C-star algebra that's left and right invariant by convolution. So those are the important ingredients for us for this reduced C-star algebra. For the compact quantum group C-star algebra. And these things have an underlying compact quantum group. So to say a bit more about that, but not really getting into too many details, is So G hat denotes a compact quantum group, and these things are in duality with discrete quantum groups. And so that's kind of like the theory going back to Vergnioux for compact quantum groups, formulated in terms of quantum group C-star algebras. I could have started with compact quantum groups and derived all of this from there. But one thing I want to get to is that there exists a universal version of the compact quantum group C-star algebra, and you build it out of some kind of universal construction. And by universality, we have a quotient map from the universal C-star algebra to the reduced one, and it respects the coproducts. In particular, we get a natural isometric embedding of the state space of this reduced C-star algebra inside of the state space of the universal C-star algebra. And it's also algebraic, so like the convolution on the reduced one matches up with the convolution on the universal one through its embedding. So this is sort of, all right. And so in the classical case, if you quantize a discrete group, so L infinity of G is just infinity of G, the coproduct is defined using the group product, and the left and right Haar weights coincide, and it's just the counting measure. And the reduced C-star algebra is the reduced C-star algebra, etc. And the Haar state is this canonical trace. It's the thing that's supported only on the trivial subgroup in terms of the group unitaries. So the Haar state in the discrete group case is always tracial, but it's not always tracial in general. And so the ones where the Haar state is tracial, we call these Katz-type compact quantum groups. And then those are in duality with unimodular discrete quantum groups, and that's where the left and right Haar weights coincide. So that's more reflective of these extra properties that's happening with the classical discrete group case. And I'll just mention that it's possible for the reduced C-star algebra to have no traces at all. So for example, for certain, these non-Katz free unitary quantum groups or free orthogonal quantum groups, they can have no traces. All right, so let's go to the quantum group dynamics. So here, what you do is you replace the idea of an action with a coaction, which is what the coproduct is to the group product. So basically, a coaction is a morphism on a unital C-star algebra going from A to this space, and it satisfies this coaction property, which is a generalization of the coassociativity property, much like how the group action law is a generalization of the associativity law for a group multiplication. And then it must also satisfy this density condition, which is sort of encoding the fact that in the classical case, you also have to ensure that the group is acting by star automorphisms. All right, so then such a C-star algebra, we will call it a G C-star algebra. And we also equip this category of G C-star algebras with G equivariant maps. So G equivariant UCP maps. And we say it's G equivariant if the map respects the coactions in the natural way. Okay, so we get sort of this quantum analog of group dynamics for discrete quantum groups. All right, and so this is how we define G boundaries in general. So a G boundary is a G C-star algebra where we have a certain rigidity on the embeddings that we have of that G C-star algebra inside of L infinity of G. So we say that it's a boundary if all of these G equivariant UCP embeddings into L infinity of G are completely isometric. And with this definition, we can also construct the Furstenberg boundary, which is the G injective envelope of the trivial coaction. And to give you sort of the classical definition, so you have G acting on some compact space, X. C of X is a G boundary, if and only if for every probability measure on X, all of the point masses can be obtained by the orbit, the closed orbit of G, acting on this measure. So given G acting on X, you can naturally have that G acts on the probability measures of X. And so the idea is more or less given two measures on the probability space of X, you can always sort of shift one to the other using the group action. So that's the idea of a boundary. And the way you encode this for discrete quantum groups is through this condition. So it's not exactly apparent from how I'm presenting this, but this is equivalent to this definition. Okay. All right, and then we can generalize convolution using coactions to get module actions of L1 of G on the dual spaces of G C-star algebras. So basically, you just write convolution of a coaction using the same sort of kind of formula that you had for convolution on say, quantum group C-star algebras. Okay? And so, kind of as a side remark, we can talk about alpha invariant states, if you will. But I'm only going to be interested in these in a very specific case. And the specific case is the quantum conjugation action, which generalizes the idea of the conjugation action of a discrete group on its reduced C-star algebra. And the way you go about this is you take the unitary that implements the coproduct, of the discrete quantum group G, and then, well, this definition naturally extends to all of B of L2 of G, this map. And so then you just restrict your attention to the reduced C-star algebra of G hat. And this gives you a coaction of G on the reduced C-star algebra. And I'll call this the quantum conjugation action. And so with this, we can talk about G-invariant states. And a state is G-invariant if it's invariant with respect to convolution by this quantum conjugation action. Okay? And in the classical case, this recovers the definition of G-invariance in that case, where you're just convolving by point mass measures that corresponds to doing that with the conjugation action. Okay? So what I'm interested in talking about then is comparing tracial states with G-invariant states, where what I mean by G-invariance is this condition. Okay? And so Kalantar al, so the same reference that I had before, they had the following result for unimodular discrete quantum groups. And it says that we get the same nice thing that we had for classical groups for discrete quantum groups. So a state is G-invariant if and only if it's tracial. And that's really nice. But it turns out this doesn't hold in general. So in general, something is G-invariant if and only if it's a certain KMS state with respect to the scaling group, and I don't really want to get into the details of the scaling group. In case you're unfamiliar with KMS states, what this means is, say mu is KMS if it satisfies traciality, but it's twisted by the scaling group. So it's sort of a twisted version of traciality. And the scaling group thing is taking into account certain modularity properties of the discrete quantum group. So we have this sort of twisted tracial condition. So it's a KMS state. And another thing that they showed is that the Haar state is G-invariant if and only if it's tracial. So this thing is G-invariant only in the unimodular case. Okay, so that's what was known from them. So let's now talk about idempotent states. So an idempotent state is a state that is idempotent with respect to convolution. For example, the Haar state is idempotent just from the invariance and the fact that it's a state. And well, it turns out that the idempotent states do satisfy this equivalence between G-invariance and traciality. So I'm sort of lumping together these two results of mine. Okay, so we get this. And it turns out, so sort of the main thing I want to talk about today is that this coincidence is enough to do interesting things about the tracial states on reduced C-star algebras. And so for instance, from this you can get that a tracial state exists if and only if a G-invariant state exists. Right, so tracial states don't always exist, but they exist if and only if a G-invariant one exists. And so I'll give you an idea of the proof of the former thing, And the argument follows from a sort of standard harmonic analytic kind of argument. So the way it goes is like this. So if you start with a tracial state, there is a canonical way of obtaining an idempotent state where you look at trizero sums of convolution powers. And then you take a weak star cluster point, and that's an idempotent state. And it's easy to see that it's also a tracial idempotent state. And it turns out that you have a similar thing for G-invariant states. But with the definition alone, it's not that easy to do it, but you can do this using the KMS characterization. And that also isn't obvious with just the KMS condition. You have to use special properties of the scaling group, but it turns out it works out more or less the same. And so what happens is if a tracial state exists, then a tracial idempotent state exists. Likewise for G-invariant states. And then idempotent tracial states are exactly the G-invariant idempotent states. So I'm going to quickly go to my first consequence of this. So nuclearity has been known for a while to have something to do with immutability. So in the classical case, G is amenable if and only if the reduced C-star algebra is nuclear. That's an old result of Lance. And we have, so a bit more recently, we have the result was generalized to locally compact groups. And we have this kind of similar problem with locally compact groups, that the reduced C-star algebra doesn't always admit a tracial state. And that turns out to be something that was important in the classical discrete case. And it turns out there, G is amenable if and only if the reduced C-star algebra is nuclear and admits a tracial state. Okay. So this is a nice operator algebraic characterization of immutability. And so just to give you a general definition of immutability, what we can do is we can say a compact quantum group is co-amenable if the reduced C-star algebra emits a character. And this is the same thing as the reduced C-star algebra coinciding with the universal one, or rather the quotient map from the universal to the reduced one is injective. So in the classical case, this characterizes amenability of G. So G is amenable if and only if G hat is co-amenable. Okay. So this is our general definition of immutability, which works for discrete quantum groups. It doesn't necessarily work beyond that, but okay. So it turns out that co-amenability of G is equivalent to nuclearity in the existence of a G-invariant state. And this was proven not long after the locally compact group case. And so immediately we get that you can replace G-invariance with a tracial state. So we get this purely operator algebraic characterization of a co-amenability of G hat. All right, for my next thing I want to discuss a bit about quantum subgroups of compact quantum groups. So given two compact quantum groups H hat and G hat, then we say that H hat is a quantum subgroup of G hat if we have a natural compact quantum group quotient map from on their universal C-star algebras. So by this I mean that it's a surjective star homomorphism that respects the coproducts naturally. And then with that, we can define a quotient. So we define the quotient of G hat by H hat to be all the fixed points of this thing. So this is sort of a quantum analog of saying that, you know, this is the algebra of things that are constant on cosets of H hat, if you will. Okay? And then we can define co-amenability of quotients, and we say a quotient is co-amenable if there exists a reduced version of the above quotient map. And in the case where H is trivial, this actually recovers the notion of co-amenability of compact quantum groups. All right, so in the classical case, perhaps a bit confusingly with our terminology, the quantum subgroups are quotients by normal subgroups, and then quotients are the underlying normal subgroups. And then co-amenability here is equivalent to amenability of those underlying normal subgroups. So the idea is that a co-amenable quotient is a quantum analog of a normal amenable subgroup. All right. So with that, okay, so suppose we have a G C-star algebra and a state on this G C-star algebra. Then we can define these Poisson maps given by these states. So their ranges are in L infinity of G. And we define the co-kernel of a coaction to be the subalgebra, the von Neumann subalgebra of L infinity of G generated by all of these Poisson maps. Okay, so classically, given a group acting on a compact space X, this recovers the co-kernel of this action. So the co-kernel is equal to the von Neumann subalgebra of L infinity of G by G mod the kernel of alpha tilde. Okay. In general, so the kernel of an action is a normal subgroup of G, and we get a non-commutative analog of this. So for a co-kernel, there exists a quantum subgroup of G hat such that it is the co-kernel of this coaction. And in the case of the Furstenberg boundary, we denote the co-kernel by GF. All right, so classically, this GF, the co-kernel of the Furstenberg boundary action, is the quotient by the amenable radical, so the largest normal amenable subgroup of G. And there's a non-commutative analog of this fact, right? So, this is the largest amenable thing, so then the quotient is somehow a minimal thing having to do with amenability. I don't want to get into the details of these terms, but this is a minimal thing having to do with amenability. Okay, and okay, so this somehow relates to this notion of co-amenability I showed you. I still don't really want to get into this, but there is a precise question underlying this, but it's unknown if relative amenability corresponds to co-amenability. And it's known to be true in certain cases, but I don't want to get into that. Okay, so going back to idempotent states, it turns out that there is a one-to-one correspondence between tracial idempotent states on the reduced C-star algebra and Katz-type quantum subgroups of G hat where their quotients are co-amenable. So classically, I mentioned this earlier, so it's a quantum analog of the fact that the idempotent tracial states on the reduced C-star algebra are in correspondence with normal amenable subgroups. Okay, so then the intuition is that these idempotent states are quantum indicator functions on quotients of the compact quantum group. So it's not true that this doesn't hold for all idempotent states, but for these ones, this is our intuition. Okay. So in general, if you have a quantum subgroup of G hat, then there's some corresponding idempotent state on the universal C-star algebra. The reverse doesn't hold. So in particular, we have an idempotent state coming from just GF, the co-kernel of the Furstenberg boundary action. And classically, this is just the idempotent state coming from the amenable radical. And so it turns out that if GF is equal to G, so this is a quantum analog of the fact that the amenable radical is trivial, then we get the unique trace property in the unimodular case. Otherwise, you get no traces at all. So this was something that was proven by Kalantar al. And I noticed that by looking at their proof, actually, in the more general setting, their proof seemed to work. If you just add a couple extra lines, and you can get this. For every G-invariant state on the reduced C-star algebra that concentrates on the quotient by this Furstenberg boundary co-kernel. And by that, I mean it satisfies the following. Whenever you convolve it against the idempotent state coming from GF, then you get this G-invariant state. So it's kind of like saying the support of tau is contained inside the support of this thing, right? And the sketch of a proof is, at least the very basic idea of this proof is just like the discrete case. So G-injectivity means we can get a G-equivariant extension onto the cross product of G with the Furstenberg boundary to the Furstenberg boundary. You can use categorical properties to prove that this is actually a conditional expectation, and then you just work a bit more and you get the final result. And in particular, this applies to tracial idempotent states because those are G-invariant from my first result here. Okay? So then what we get are the following consequences of that. Okay, so first, given quantum subgroups of G hat, the lattice structure corresponds to this natural lattice structure on the idempotent states that are associated with them. Okay? And so it turns out, giving any Katz type quantum subgroup of G hat with co-amenable quotient, then this G hat is a quantum subgroup of that thing. So again, this is sort of a different quantum analog of the fact that the co-kernel of the Furstenberg boundary is a minimal thing in terms of amenability. But the thing I need to note is that, well, okay, it's minimal in the category of these sort of things, but itself might not be Katz type, and its quotient might not be co-amenable. Well, okay, it's unknown if its quotient is co-amenable. Okay. So strictly speaking, I don't need to introduce this, but it makes the next thing I'm about to do a bit nicer. Okay, so it turns out that there exists the largest Katz type quantum subgroup of G hat. Let's call it G hat Katz. It satisfies the property that for every Katz type quantum subgroup of G hat, it's a quantum subgroup of this G Katz thing. Okay, so if you assume this quotient is co-amenable, it's unknown if that always happens, then it turns out that the reduced C-star algebra emits a tracial state if and only if this GF hat is Katz type. And the proof is really simple, and this is what it is. Okay, so this emits a trace if and only if this quotient by the canonical Katz quotient is co-amenable. That's not too bad to prove if you know some of the basic theory here. By minimality, GF hat is a quantum subgroup of G Katz, and then more or less by definition, this forces it to be Katz type. So it's a pretty simple argument. Yeah, so that's everything I wanted to talk about today.
Are there questions or comments? Hey, is somebody still awake?
So even in the Katz type case, we don't know if G over GF is co-amenable.
No, we don't know. I guess we only know if yeah, we don't really know anything at this point.
But are there examples where we are able to decide whether it is co-amenable?
I guess if GF is the whole thing, or if it's or if it's trivial, but yeah.
Create like a ln plus, or ln plus, or something like this.
So in those cases, it would be the whole thing.
Ah, okay.
Yeah. Yeah, it's hard getting it's really hard getting non-trivial examples of that.
Okay, if there are no further questions, then thank you, Benjamin.